Hello again, statisticians. Last time we revealed the knowledge of the ages in the form of estimation, statistical estimation, and the awesome power of sampling. And we saw from some relatively small samples, we can make some very accurate conclusions and estimations about a population of interest or a market segment of interest to us. So last week's subject was statistical inference again. So from this unknown population, this nebulous group out here, we draw some individuals and query them about whatever it is we're tracking. And from this known result, from the few, how do we generalize to the many? That's statistical inference. Last time our definition of to infer was to estimate, to forecast, or predict. Our definition tonight and our new topic will be what can we prove? What can we conclude about the populations? Now, what do I think? What can I prove beyond a reasonable doubt is our subject, new subject for tonight. Well, let's take a look at some practice problems from last time where we did this very useful, very useful topic. And of course, it all hovered around page 24. And our first bit of practice was to stare at page 24 until it made sense to us. If we collect quantitative sample, then I'm either estimating mu, the average of everybody, or the total, the sum of all of the observations across the entire population. If I have qualitative guess data, I'm trying to guess P, the proportion of people across the population with some attribute, and or the total number of individuals across the population who are going to have that attribute. Of course, this is a big one that's in all our political polls that we bombarded with daily on the cable channels. This is what they're using, this picture right there, to make their statements about the accuracy and the error factor of that particular poll. All right, so everything's there. Everything we need to know about this topic is on this page here. Last time we didn't discuss the fruit cocktail down at the bottom here. We will. We'll make mention of it tonight so you have a complete coverage of everything there. So our first problem was on page 25, number 3. Got a government testing agency assigned the task of estimating the average nicotine content in a new cigarette called Philip Morris. I got to change this to be vaping, of course, but it's still a good name for a vaping product, Philip Morris. So next edition of the book, that'll change. If you know a better name for the product too, let me know. I'm always interested in finding something more offensive. A sample of 400 cigarettes yielded a sample mean of 19 milligrams of tar and of nicotine, and sample standard deviation of 2 milligrams of nicotine. Construct a 68% confidence interval. Give me something tough. When I sample over 30 and it's a 68% confidence interval, I know it's just plus or minus one step, one standard deviation. So what do we know? I really know nothing about the population. I don't know how many cigarettes they've ever produced, maybe a million or billions. I'll never know mu. Some fool out there has already smoked some of them. I'll never be able to do a census. And I'll never know sigma because I'll never be able to do a census. I took a sample of 400, found average of 19 and a sample standard deviation of 2. So just do this on the final. You'll let me know exactly what you don't know, what you know. You've categorized everything for me, so I know if you make a dumb error, it's not a conceptual error. So here we're asked to estimate the average nicotine content of all of these million or billion cigarettes that they've produced based upon our sample of 400. So we head to page 24. Quantitative data, guessing mu, the average of all 4 billion cigarettes. Best guess is, what we see in the sample mean is our best guess at what the population mean is. Is it exactly equal to that? No. But the smaller the variability in the population and the larger the sample size, the closer it is. If we have a very diverse group, big S, that's a problem. If we take a small sample size, that's a problem. But if we have small s and big N, we're going to get very, very accurate predictions. So I take these back. I have a bell-shaped curve centered at 19, and our shape is 2 over the square root of 400, which is 0.1. So I can confidently say I'm 68% sure that the average nicotine content of every cigarette ever produced by this company is between 18.9 and 19.1, plus or minus one of these. This is our step size for this particular picture from page 24. 95% sure it's 18.8 to 19.2, and bet my job it's 18.7 to 19.3. Easy peasy. Dr. Cyclops, page 28, number 15, noted optometrist prepares contact lenses and regular glasses for his customers. Size popular, book solid with 900 appointments over the next 3 months. Took a random sample of 36 of people with appointments, and it was determined that 24 of them were coming in for contact lenses. Okay. So what question was asked 36 times? Hello? Calling for Dr. Mal, confirming your appointment. And oh, by the way, are you coming in for contact lenses? And I got back responses of yes and no, yes and no. I got back 24 yeses, 24 yes, I'm coming in for contact lenses. So this is qualitative data. Well, what do we know? Qualitative data. We have a population of 900. Turns out we're going to be ordering for the next 3 months. So that's our population of interest. How many are coming in the next 3 months wanting contact lenses? And that's what I need to order for. Will I ever know P? Yeah, I'm going to do a census. I'm going to treat all 900 of them. And I'll be able to tell you after the fact what P is, what proportion of the 900 are coming in for contact lenses. Took a sample of 36, 24 yeses out of 36 for 2/3 or 0.67. Part A, construct a 90% confidence interval on the actual proportion of the 900 who are requesting contact lenses. So I go to the control tower here on page 24. This fabulous handout that our dear and beloved prof has given to us. Qualitative data, guessing P, the proportion of all 900 who are going to come in for contact lenses. Best guess is 2/3, what I saw in the sample. Here's my shape, if you will, the step size of this normal curve. I did sample over 30 again, so it's a regular old Z curve. In the first problem I did, I sampled over 30, so it's a regular old Z curve. So I need to bring back that. So my uncertainty is a normal curve centered at 0.67 with a shape of, what does it turn out to be? 0.67 times 1 minus 0.67 over 36. Of course, on the exam, you'll leave it just in that form. Now, since it's not a 68, a 95, or a 99, I got to go to the tables unless you happen to memorize a 90% confidence interval. On a 90% confidence interval, I'm 90% sure that my 2 bounds, that the true population proportion is within those bounds, but there's a 10% chance that it's not in those bounds. So 1 minus 90% is 10%. And we split the error factor in half. there's a 5% chance it'll fall below our lower bound and a 5% chance it'll fall above our upper bound after we get done constructing our confidence interval. So I head to my tables, and I say, okay, find me the normal table. Find me the 5th percentile. I know I don't need to go over this because we've all learned the normal distribution. And if we haven't, shame on you. There's 0.0505. All right, and 1.64, 1.65, probably better to use the 1.65 to get you a little wider interval, more conservative. So minus 1.645 would work. So I'm going to step off. Yeah, I'm looking for 90, so I look up 0.05. Or I can look up 0.95 on a 90% confidence interval. It is the 5th percentile and the 95th percentile, yielding 90% of the area in between the two bounds.
But I was looking for 90.990, and I got like.
Yeah, that would work if you're doing an 80% confidence interval.
0.15, which is like 2.29.
Nope. All right, so on a 90% confidence interval, we're going to have 5% in the left tail, 5% in the right tail, and 90% in between, correct? So when we look up in our tables, I can look up the 5th percentile. That'd be the lower bound of the table of the curve.
So I look for the tail, or I look for the.
No, you look for the tails. 0.05 is what we look at, or you could look up 0.95. That would work also. So what is a 90% confidence interval? The lower bound is the 5th percentile. The upper bound is the 95th percentile. So that, how much do you have in between? 90%. All right, so I'm going to step off 1.64 to the left or right, or 1.65. And that's my starting point, that's the center point, and there's the shape of the curve. Part 2 asks, how many pairs of contact lenses should we order to be 90% sure we have enough? Okay, so this is the difference between a 90% confidence interval and a 90% tile, a 90% tile. What is a 90% confidence interval? I think the portion of the population is 0.67, could be as low as 0.67 minus 1.64 times that, or could be as high as 1.67 plus 1.64 times that. What is a confidence interval? It is a 3-number answer. Your best guess, 0.67, a lower bound, and an upper bound. It's 3 numbers. So when I make a forecast, I use a confidence interval. I think it's here, could be as low as here, or as high as here with 90% certainty. When we get to part B, and we're going to call up an order. Hello, I'm calling for Dr. Tsai. How many numbers am I going to transfer? Am I going to communicate to the person on the other end of the line? 1 number. You know, how many you want to order? You know, you're not going to say, well, I think it's 0.67, or it could be here, it could be here. They want 1 number. What's the number? That's a percentile, a 1-number answer. So I go to my control tower, and here's my control tower. Here's my control tower. and I'm trying to guess this one right here, the total number of contact lenses needed for all these 900 people. My best guess is I need 600 times 2/3. I'm sorry, 900 times 2/3, or 600. And here's my uncertainty. Okay, here I did a lower bound, my best guess, a lower bound and an upper bound. That's what I do for forecasting. Here, when I go to order, one number. I'm only going to supply them one number. And for whatever reason, because of the economics and the problem, we chose the 90th percentile. When you take SOM 686, you'll cover how do you find out what's the optimal, that the optimal is 90, and they'll show you a little trick you can do, and it gives you the optimal percentile. Slick little thing. All right, so find me the 90th percentile. I head to my tables, find me the 90th percentile, 90th percentile, 90th percentile, oop, too far. Go back, 90th percentile. Yeah, take either one of those, I don't care. But technically we should be taking the first one bigger than or equal to. Always err on the side of being too conservative, of ordering too much. So 1.28 or 1.29 steps to the right of the center point. So I start at 600, walk 1.29 steps, and here's your step size from page 24. So is that clear on the difference between a confidence interval and a percentile? See me at the break and we'll draw some pictures. All right, that's one thing I could stop it now. Okay, stop it now as well. Okay, onward. Geriatrics, I'll be there right after I grade all of your papers and exams. I'll be at the Reseda Home for the Aged if you want to come by and see me. I've been scouting it out. We have 500 people live there. Jerry orders prunes every week for the resident. Took a sample of 8 residents and determined how many prunes they ate. You can't ask them because they can't remember anything. You gotta watch them and count them as they eat them, you know. And we got the following results. Not much variability there. They all eat a lot of prunes. That's about what, 10 a day if this is for a week, I would hope. A week, yeah. Okay, so only 10 prunes a day. All right, so this is a little descriptive statistics problem. I would not ask you this many points. Your descriptive statistics problem on the final have 4 or 5 points max. So first thing we do is sort the data. Out pops the median is 70. The mode is 70. The median falls halfway between 70 and 70, so it's also 70. And we add them all up and divide by 8. And we get sample mean is 70. So this thing was, since the mode equals the median equals the mean, is probably symmetric. Probably symmetric. And then we find the sample variance. We take each of the observations, subtract the 70, which is our sample mean, square them, add them up, divide by 8 minus 1, which is 7, and we get our 4. So on the exam, I'll ask you to do this, and then I will give you a check figure for your S to use going forward. So you can leave the numbers in their raw form, and then remember that when you do the evaluations on me, okay? That I did that for you. Yes, question? Pardon? This is definitely quantitative. Can I do arithmetic with the numbers 71 and 72 and 69? Yeah. let's see, this is 69 is 3 less than that, and 2 more than, and 68 is 1 less. They're numbers. It is quantitative. I mean, can you do arithmetic with these numbers? Sure can, right? Qualitative data are things like yes, no, and brands and stuff like that. All right, so that ends the descriptive statistics part. Then let's construct a 90% confidence interval. Oh, good, a 90. We just looked that up. It's plus or minus what? 1.645, right? Uh-oh. But what? We didn't get enough sample size in order to use the regular normal distribution. Okay, so life sucks. Notation. We have quantitative data. I have a population with 500 residents. Will I ever know mu? I guess you could if you wanted to keep track of the total prunes consumed by all the residents over the next week. And then you could find sigma if you really wanted to. It'd be a lot of work, but you could. Sampled 8, got an X bar of 70 and S of 2. Okay, we're asked to do a confidence interval, a 90% confidence interval, so my error factor is 10%. Alpha is the error factor. Okay, we really don't need that right now, but we're going to need it, and as soon as we start our new topic tonight, we'll need an alpha, and it represents an error factor. So this kind of just greased the skids for us into that topic. I split the error factor in half when I do a confidence interval. So I need to head to this is saying, we're at this picture right here. I've got sample size less than 30. Okay, so it says everything's the same center point, same step size, but now you got to go to a different table because a t distribution is a squished z, okay? And when you have a sample of 30, the t and the z are almost traces of each other. That if it's significantly less than 30, which 8 is significantly less than 30, we're going to have to introduce a larger fudge factor when we do our confidence intervals because of the additional uncertainty we've introduced because of this small sample size. So I head to my tables and I find the t table on page T14. I want the 0.05 column. I want the 5th percentile. And then I go to row 8 minus 1 or 7. The basic rule is whatever denominator you use to find your sample standard deviation or the equivalent of your sample standard deviation is the number of rows you use. And when we divided, our sample standard deviation formula has us dividing by n minus 1. So instead of stepping off 1.64 like we did in the previous problem, we're going to need to step off 1.895 because of our small sample size. So we do that. We start at 70, walk 1.895 to the left, 1.89 to the right, and your step size is the 2 divided by the square root of 8. 2 divided by the square root of 8. There is the step size for this particular picture. All right, so that's, yeah. Part C, something new. We haven't done this before. How many prunes? We've done this before. How many prunes should we order to be 99% sure we have enough? Okay. So this is not a confidence interval. This is a 1-number answer. Part B was a confidence interval. It's a 3-number answer. I think the average consumption of prunes is 70. Could be less, could be more. I'm 90% sure it's between 70 minus the 1.895 to 70 plus the 1.895 is the upper. Here, I want to be 99% sure we got enough prunes. We don't want any, any irate old people around. They're difficult to herd. All right, so here's my picture. I'm shooting for the total number of prunes I need. Again, my sample size is 30. So I'm going to take my 70 prunes times my 500 residents. What's that, 35,000? And that's my best guess. And then here's my step size. 500 times S over the square root of N. So I take my 500 times the 70, that's 35,000. Now I need to know how many steps I go to the right. Okay, I want to be 99% sure I got enough. And so I'm in the 7th row here. I need to step off 2.998 steps to the right of the 35,000. And then here's your step size here. Oh, that's the step size. And that's again from page 24. All right, here's the new thing. We haven't done this before. So, you know, it's a 3 or 4, you know, it's a few years from now, you've got your MBA and your boss says, okay, we're trying to figure out what's going on in this marketplace. What should we do? And you, me. Let's take a sample. Because of the awesome power, this thing, awesome power of sampling is still, you know, echoing in your in your head. I won't tell you why it's echoing. Little joke there, okay. Jeez. I was kind to you on the midterm, wasn't I? All right, and so the boss says, oh, fabulous, let's do that. How many should we sample? And you go, let me go check. And you whip out page 24, because you laminated it. You keep it with you. You're always prepared. All right, so let's look at down here. Here's your sample size formulas down here. Okay, here's the formula for when you got quantitative data. Here's the formula when you got qualitative data. We got quantitative data, so it's this one here, and that's what I transcribed onto here. Here's the formula. So what we're doing when we specify a sample size is we're specifying the confidence interval's width when we get done. We're saying what size confidence interval is it? In this case, it's a 68% confidence interval. And it has a width of what? 0.2 prunes. The plus or minus distance is your width, is your fudge factor, your error factor, your distance, your tolerance. That goes in the denominator. You put your 0.25 there, squared. Okay, I'm going to, when I'm done, want to be 68% sure I'm within that distance. 68% is plus or minus 1 standard deviation. If it was a 95, you'd put in 2 here for this term. 99, you'd put in 3. 90, you'd put in 1.645, okay? And then lastly, you put your sample variance. And then you say, well, how do you get a sample variance? You have to do a little pilot study of a few individuals and get a rough idea where the sample standard deviation is. All right. So why did we use the Z here? The assumption is that the sample size we're going to get is going to be greater than 30. So then it would be appropriate for the Z. If it turns out to be less than 30, then then you got a problem. And you have to tweak it, but almost always it is greater than 30 when you get done. So when I take this sample, boom, 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 turns out we need to sample 64 individuals. Okay, so here's the formula. It's got 3 parts to it. Okay. The plus or minus distance we want goes in the denominator. Okay, how sure do we want to be? What size confidence interval are we going to form? We're going to form a 68% confidence interval. So that's plus or minus 1 step there. And then the S value you got when you had your little preliminary sample. Okay, but yeah. Where's the which? The 0.25?
Yes.
It was given in the problem. We want to be within what distance? Plus or minus 0.25 prunes. All right. But there's one thing I need to tell you. When you are done taking your sample of 64, when you go to construct the confidence interval, your population has, what, 500 people in it? And we are going to sample 64. We're sampling what? 13, 14% of the population, aren't we? 10% would be 50 or over 10%. And the good news is, if you sample more than 5% of the population, that's what this is saying here. If you sample over 5% of the population, then you're even more accurate than you were before. And you take whatever one of these 4 pictures we have for your step size, and you multiply it by this, which would be 500 minus 64 over 500 minus 1, which is a number smaller than 1. So we are reducing our step size, meaning we're more sure. So it doesn't matter if the population, if we sample 100, if the population's 10,000, 10 million, or 10 billion, we are exactly as accurate estimating each of those. The population size doesn't matter as long as you don't sample over 5% of the population. Then you got to make an adjustment because you're even more accurate than you were before. You know, most people think, well, if you sample 100 out of 10,000, you're much more accurate than sampling 100 out of 10 million. That is not true. They're equally accurate. They're infinitesimally close. Okay. Again, when I go to do my confidence interval, my step size is going to be reduced because I'm going to multiply it by this factor here. Most always our population sizes are very large or huge in comparison to our sample size. So this is not an issue, but when it is, the good news is we're more accurate. One of the problems in the book, I think I show you how to do it. There's one of the problems, I'll look it up at the break and tell you which one. I show you how to do this. Okay, so onward and upward, and to our last problem, which is on page 28, number 14. Snorettes is a sleeping aid developed by a major drug manufacturer. Snorette's so potent and effectiveness, it's been compared to watching 10 minutes of the Rosie O'Donnell show. You know, there are these things that just you cannot explain. You know, like, what purpose in life does my brother-in-law serve? I have no idea. I cannot, it's always confounded me. And then the other is, how did Rosie O'Donnell get to be rich and famous? You know, I know she was in the original Grease on Broadway and all that. I don't get it. I'm just jealous, that's all. The FDA is concerned, however, that some people have an allergic reaction to it. Okay. The drug was tested on 900 randomly selected individuals, and 90 showed an allergic reaction. In the good old days, before lawyers screwed it all up, where did we get all of our individuals to volunteers for testing of medical testing? Where did we get the human volunteers to do it? The prison system. You want an early parole? Do something for mankind. Do this little test. So you grow a third arm. We'll cut it off for you. But no, lawyers got in there and screwed it up. And so they don't go do. So they went to some individuals even further lower on the food chain than convicts. Most of the participants in medical trials are what? Mice. Are what? Mice. No, human trials. The mice died first, and then some of the other the higher primates maybe. Come on, what's lower than a college student? College students, of course. College students, you want to make tuition this semester? Well, just a little test, a little drug, and 50% chance you get the placebo, right? So, yeah, so most of the testing is done at teaching institutions, and the people that are available are students. And some of them get a lot of money. All right, so we got this population. I mean, who are candidates for this drug? I don't know. Everybody? I don't know. We don't know. We don't know the candidates are across the entire population of the world for this drug. Are we ever going to know what the proportion of the entire world is who's allergic to this drug? No. Took a sample of 900. Okay, what was the question we asked? Hey, you on the floor. Are you having an allergic reaction? Hey, put a mirror on his nose. Let's see if he's having an allergic reaction. Yeah. And 90 out of 900 said yes. So we have a significant problem. This one is not going to make it through testing. I mean, they're tracking for fractions of 1% for reactions, in the trials, not 10% of the people. All right, here we go. Establish a 95% confidence interval on the proportion of people in the world who are allergic to the drug. Okay. We sampled over 30, so 95 is just going to be plus or minus 2 steps. So we go to our picture here. Here's my target. I'm saying find me the proportion of the people in the world who are allergic to the drug. Sampled over 30, it's a regular old Z curve. Okay, best guess is 10% of the people in the world are allergic. Here's the step size for my confidence interval. So just plug those values in, wham, bam. Easy 5 points on the final. How much larger a sample is needed to estimate the population proportion within 1%, plus or minus 1%, with 95% accuracy? Oh, let's go here. Here is the formula for sample size when we have qualitative data. Qualitative data. Oh, there it is. I brought it over here. So, again, I have what size confidence interval are we going to form? In this case, we're going to do a 95% confidence interval. 95% accuracy, 95. So that would give me a Z value of 2. 95, give me a Z value of 2. My tolerance, when it's qualitative, is also a percentage. So that's kind of a little confusing, but no. The plus or minus distance is the tolerance, is the bounds. If your distance is at plus or minus 1%. So that's what goes in the denominator, and it's your 1%, 0.01 in the denominator. And your, what's the p-hat that we saw in our initial study? Our p-hat was 0.10. So I'd take 0.10 times 0.90, and when the dust settles, I get 3,600. Why is it so high? Quantitative data, sample sizes are relatively small, 50 to 100, usually are sufficient. Qualitative data, what you are trying to predict has the ultimate variability. It's yeses and nos, zeros and ones. And so you need much bigger sample sizes for qualitative data. Typical poll size on, they use in the newscasts on scientific polls is at least 2,500 because it's qualitative data. In this case, you want to be that accurate, it's 3,600. So we have the situation here again where we need a little pilot study to get a p-hat, a guesstimate of where p-hat is in order to form the sample size formula. If you don't get any data, if you can't get any pre-samples before the study, then you plug in 0.50 for p-hat, because that's the biggest a number times 1 minus that number ever gets to be. You plug in 0.5 if you cannot get a little pilot study going to get your p-hat. Okay, why is that? I'm taking a number that, first, p is less than 1. So I take a number that's less than 1 and times 1 minus that same number. If I multiply 0.1 times 0.9, what do you get? 0.09. 0.2 times 0.8, you get 0.16. That's bigger, right? 0.3 times 0.7, 0.21. 0.4 times 0.6, 0.24. 0.5 times 0.5, 0.25. 0.6 times 0.4, 0.6, 0.24. It starts going down again. So your 0.5 times your 0.5 is the biggest it ever gets to be. So you're very, very conservative when you do that. All right. Any questions at all on statistical inference? We should put that in the camp as a friendly problem, a friendly topic. I don't think we should be afraid of that on the final exam. All right, our next subject is hypothesis testing. Those of you who've had some kind of statistics before, just the mention of the phrase hypothesis testing often makes us shudder uncontrollably, because this is a horrible topic. This is why statistics has a bad name, is this topic here. But once again, your wonderful, all-around swell guy, professor, has taken care of his flock and has given you a handout. The previous world record for covering hypothesis testing is 2 hours. We're going to go for 20 minutes, okay? 20 minutes, okay, is my objective. I called Guinness, and they just wouldn't send anybody out to see Sun. I don't know why, but I told them what I was going to do, but they wouldn't send anybody out. Okay, so that is my teaser. Let's take a brief break here. This is a logical point to take a break.